In section 4.3, we're going to look at increasing and decreasing functions and the first derivative test. One of the important definitions we want to recall from college algebra is that of an increasing and decreasing function on an open interval. A function is increasing on an open interval I if for any x1 and x2 in the interval such that x1 is less than x2, it implies that f of x1 is less than f of x2, then the function is increasing on that interval I. The condition that x1 is less than x2 simply means that we would read, for example, the graph as we would read a book. We're going from left to right. And if the function value on the left-hand side is less than the function value on the right-hand side, in other words, if the graph appears to be moving in an upwards manner, then that function is increasing on that interval. Conversely, a function is decreasing on an open interval I if for any x1 less than an x2 in the interval with x1 less than x2, if we have f of x1 is greater than f of x2, then the function is decreasing. Again, the basic concept here is if you look at the graph of the function, if we read it going from left to right, if the graph is moving in a downward manner, then the function is decreasing on that interval. We know that from previous sections that the rate of change is related to the derivative. And one of the things that we're going to see is that when a function is decreasing, if it's differentiable, then its derivative will be negative or less than 0, meaning it has a negative rate of change, it's decreasing. If the function is increasing, then it has a positive rate of change, which means that its derivative is 0. And we didn't write the constant case down here, but if f of x1 is equal to f of x2, for all x1 less than x2 in the interval, then the function is constant. Graphically, what that would look like is it would be a part of the function that's horizontal. And if it's horizontal, then it's not, function values aren't changing, which means that its function values would be constant, which means its derivative would be equal to 0. This brings us to theorem 4.5, the test for increasing and decreasing functions. Let's let f be a function that is continuous on the closed interval and differentiable on the open interval a to b. If the derivative is greater than 0 for all x in the interval a to b, then f is increasing on the closed interval a to b. Technically, it probably should be an open interval here. If f prime of x is less than 0 for all x in ab, then f is decreasing on ab. And if f prime of x is equal to 0 for all x in ab, then f is constant on the interval a to b. So very important, positive derivative means the function is increasing, negative derivative means the function is decreasing, and if the derivative is equal to 0 in the interval, then that means that the function is constant in that interval. Let's take a look at example 1. We're asked to find the open intervals on which the function f of x equals x cubed minus 3 halves x squared is increasing and decreasing. According to our previous theorem, we want to classify this based upon the derivative. If we compute f prime of x, the derivative of x cubed is 3x squared. The derivative of negative 3 halves x squared should be minus 3x. So this is our f prime of x. What we're now going to do is we want to figure out exactly where is this derivative going to be equal to 0 at. Or potentially where is it undefined. We want to look for those critical numbers. Well, f prime of x is equal to 0 precisely when 3x squared minus 3x equals to 0. It's a polynomial equation. We can pull out the GCF. We can factor out a 3x. That'll leave us with an x minus 1 equals to 0. Set each factor equal to 0 independently. We get 3x equals to 0. X minus 1 equals to 0. Divide both sides by 3. We get x equals to 0. And add 1 to both sides. We get x equals to 1. These two values represent where the derivative is equal to 0. This function, f prime of x, is a continuous function. It's just a polynomial for the derivative, which means that it satisfies the intermediate value theorem. So in order for the derivative to change signs, it has to pass through a 0. Namely, it has to pass through either x equals to 0 or x equals to 1. Which means if I go to like a sign chart on this, which is what we're going to do a lot in this section, I have two numbers. Those two numbers, when I plot them on a number line, will divide the real number line up into three different regions. I have region 1, which is the region to the left of both of them. I have the open interval that's between the two of them. And then we have the open interval that is to the right of both of those values. What we want to determine is what is the sign of this derivative in any one of those intervals. And to do that, what we're going to do is pick a test point. For example, in region 1, I need values of x that are less than 0. So maybe I'll use as a test point x equals to -1. If I plug x equals to -1 into the derivative, f prime of -1, this is going to be equal to 3 times -1 squared minus 3 times -1. That's going to be 3 plus 3, which is 6, which is greater than 0. The actual value itself is irrelevant. We just need to know what the sign of it is. And what we found is the following. Since f prime is greater than 0 at the test point in region 1, then that means that the derivative will be positive for all values of x in this region. So f prime is greater than 0, which means that f is going to be increasing on region 1. Let's repeat this for the second region. I need to pick a value between 0 and 1. Let's maybe use, let's say, I don't know, x equals to half. F prime of a half, this is going to be equal to 3 times a half squared minus 3 times a half. That's going to be equal to 1/2 squared is 1/4. 3 times a fourth is 3/4. 3 times a half is 3/2. And then 3/4 minus 3/2 after getting common denominators should leave us with -3/4, which is in particular a value that's less than 0. So we see that at the test point, the derivative is negative, which means that the derivative will be negative for all values of x in between 0 and 1, which means that the function f will be decreasing between 0 and 1. And now let's figure out what's going on in region 3. We need a value that's bigger than 1. Let's use, let's say, x equals to 2, and plug that into the derivative. F prime of 2 is equal to 3 times 2 squared minus 3 times 2. 2 squared is 4, 3 times 4 is 12, minus 6 is equal to 6, which is again greater than 0. So the derivative is going to be positive in region 3, which means that the function f is increasing. Whenever we state our final answer, remember this is going back to the original function f, the question says on which intervals is the function f increasing? Well, f of x is increasing on, first of all, it's increasing on region 1, which is from -infinity up to the x value of 0. The 0 will not be included here because technically we know that the derivative is 0 at x equals to 0. So it's kind of where it changes from increasing to decreasing in this case. The function is decreasing in region 2. That's from 0 to 1. And then it's increasing again, so union increasing from 1 to infinity. Just to kind of recap what it is we did, these are going to be the guidelines for finding the intervals on which a function is increasing or decreasing. Suppose we have a function that's continuous on the closed interval a to b. To find the open intervals on which the function is increasing or decreasing, we're going to do the following steps. We first locate the critical numbers of f in the open interval a to b and use these to determine the test intervals. Notice that if you go back to our earlier definitions of a critical number is a value where either the derivative is equal to 0 or where the derivative is undefined. In the example that we just looked at, this function, clearly it has some places where f prime of x is equal to 0. Those were at x equals to 0 and x equals to 1. However, because the derivative was a polynomial, it will be defined for all values of x. So we didn't get any critical numbers of the second type, which would be the places where the derivative would be undefined, although on occasion for certain functions that will certainly occur. But step 1, locate all of the critical numbers of f in the interval a to b. That involves taking the derivative, setting it equal to 0, and also seeing where the derivative is undefined. Once you solve for those values of x, we are then going to determine the sign of f prime at one test value in each of the interval. The thing that's nice about the derivative is that it will have a consistent sign in between those values that we found from part 1. So all we need to do is take a test point, any test point at all within each interval. Whatever the sign of the derivative is at the test point, that will be the sign of the derivative throughout that entire interval. And then we're just going to use theorem 4.5 to determine whether f is increasing or decreasing on each interval. Remember, if f prime is greater than 0, then f is increasing. If f prime is less than 0, then f is decreasing. One of the other things that we can get out of this, using the first derivative test, is whether or not our critical numbers give us a relative max or a relative minimum. This is going to be theorem 4.6. Let's let c be a critical number of the function f that is continuous on an open interval I containing c, and that f is differentiable on the interval except possibly at c. Then f of c can be classified as follows. If f prime changes from negative to positive at c, then f will have a relative minimum at the pair c comma f of c. So let's think about what's going on there for a moment. If the derivative changes from decreasing, because its derivative was negative, so it's going down, it then stops at c, and then it's going to go on to increasing, the net effect that that's going to create will be a minimum at the order pair c comma f of c. Conversely, if f prime of x changes from positive to negative at c, so it's going up, it's increasing, derivative is positive, at the value c, it's now going to switch to be negative. The effect that that's going to create is it's going to give us a relative maximum at c comma f of c. Another possibility is that maybe the derivative has a consistent sign on both sides of c, meaning it's maybe both positive or both negative for the sign of the derivative on either side of c. And in that case, we don't get any relative max or relative min. This is kind of displayed by the bottom graphs here. If I take a look at this graph right here, the function is increasing from a to c. We momentarily get a place where the derivative is 0 because there's a horizontal tangent line here. And then immediately after c, between c and b on that open interval, the function is increasing again. And as a result of that, there is no max or min. Similarly, if we look at the graph directly beside it, to the left of c, the derivative was negative, so the function was decreasing. It's 0 at c, and then to the right of c, it's decreasing again. So the derivative has a consistent sign on the left and the right. Without that sign change, we do not get a relative min nor a relative max.